So in this video, we'll try to understand how to measure relationships between random variables. Let me explain what I meant by relationships. So for example, imagine I have a random variable h, which takes values of heights of students in a class, and let's assume I have a random variable y, which takes weights of students in a class, right? And let's assume I have made some observations or I have collected data as follows, right? So I have my x, which is my heights, and I have my y, which are my weights. And I take students from the classroom, and for each student, I measure the height and weight. Let's assume I get student 1 who has a height of 160 centimeters and let's say 62 kilos. And the second student that I measure, let's assume I get a height of 150 centimeters and 54 kilograms, so on and so forth, right? Suppose if I've made n such observations, right? Let's assume my nth observation is 140 and 48, right? So if I've made n such observations, the question on my mind is there a relationship? Is there a relationship between x and y? Remember, x and y are not collected independently. For every student, I got two parameters about him. One is height and weight. So this weight that we have is for the person who has this height, right? I didn't collect it this way. I didn't collect it where I took student 1, I measured all heights, and then I took a random other sample of students and measured their weights. I didn't do it that way, right? For every student, I measured their height and weight, right? So now the question on my mind is there a relationship between x and y? And by relationship, what I mean is, as x increases, can I say y also increases? Or can I say as x increases, y decreases? Because these types of relationships are important to understand because they tell us if two variables are related in any way, right? Now, how do we quantify such a relationship? So there are three measures to quantifying such relationships. Of course, each of them with their own pros and cons. The first measure is called covariance. As the name suggests, it has some relationship with variance that we learned when we learned about mean, variance, and standard deviation. And the second idea is called Pearson correlation coefficient. Pearson correlation coefficient. And the third way of measuring it is called Spearman rank correlation coefficient. All these ideas are very, very related amongst themselves. So I'll go one by one. Of course, covariance being the simplest one with its own fallacies and problems, and we'll try to correct some of them using Pearson correlation coefficient. And whatever problems Pearson PCC has, we'll try and correct some of them using rank correlation coefficient. So now let's go and understand covariance first, right? So let me define the mathematical equation for what a covariance between two random variables is. So covariance between two random variables can be written as, so suppose if I have n observations of random variables x and y in pairs is important, then I can say that this is nothing but the average value of, if I have to read this in English, right? This is nothing but average value of, right? I have xi minus mu of x. Let me just put it this way, multiplied by yi minus mu of y. So here in this equation, mu of y is the mean of y, mu of x is the mean of x, right? And you're summating it across all i's where I goes from 1 to n. Now you might ask, why does this work? This looks very similar to your formula for variance, right? What is your formula for variance? Variance of x is nothing but 1 by n summation I equals to 1 to n xi minus mu of x multiplied by x of I minus mu of x. Or in other words, it's nothing but xi minus mu of x square, right? So variance actually looks like this, right? Except that when you're doing covariance, you replace the second term. What we did is we replace the second term with yi minus mu of y. So I can write it by just looking at this formula. I can say covariance of a random variable x with itself is nothing but variance of x, right? By just looking at the formula, we haven't even understood this formula yet. But even without understanding, as I told you a while ago, the covariance has a relationship with the variance, right? Which is this. Covariance between x and itself is nothing but the variance of x. Now let's try and understand how this formula pans out, which is very important. And how does it measure relationship between two random variables? I'll try to convince you graphically with a simple plot that that covariance between two random variables is going to be positive if we have a relationship like this, where if x increases, let's say y also increases, then my covariance between these two random variables is going to be positive. Similarly, I will try and convince you that covariance between two random variables x and y is going to be negative if as x increases, my y decreases. Right? Let me convince you of this property. This is an important property to have, right? Because by just looking at the sign of covariance, whether it's positive or negative, I can tell you uh, uh, whether as x increases, y increases, or does it decrease. Now let's look at a couple of examples here. So let's say I have a data set like this, bunch of points. Okay, let's assume this is my x and this is my y. Okay, let's assume this is my mean of x, right? Because if I just project all of these points here, this is where my mean lies, right? And this is my mean of y. Okay, this is one case. The other case that we will look at is, let's assume I have a case like this. I have my x here, my y here. Here in this case, what's happening is as x increases, y also is increasing, roughly, of course not perfectly, but roughly. If you just look at the shape is going up like this, right? Now let's take another case where it's exactly the opposite, where as x increases, let's say y reduces. So here will be my mu x, here will be my mu y. And let's go and look at the formula for covariance. What's my formula for covariance? Covariance of x comma y is nothing but 1 by n summation over all the points xi minus mu of x multiplied by yi minus mu of y, right? Now let's see what happens here. So let's take a bunch of points here. Suppose if I have a point here, okay, which has its xi and yi, its xi will be here, its xi will be here, and its yi will be here, right? Let's assume this point is xi and yi. Let's say x1 and y1, just for simplicity. Here is my x1 and here is my y1. Now, if I compute x1 minus mu of x, this part of the equation, right? This will be positive for your x1, y1. Similarly, your y1 minus mu of y will also be positive, right? So when I multiply two positives, I get a positive. Simple. Now let's assume I have my x2 here. Let's assume my x2 is slightly less than my mu of x and it's slightly less than my mu of y, right? Let's assume this is my x2 and this is my y2, right? So what happens to my x2 minus mu of x? It's negative, right? What about my y2 minus mu of x? It's also negative. So negative multiplied by negative will be positive. But remember, this positive is much more positive than this. So this value that we got for x1, y1, this is what we got for x1, y1, right? This is for x2, y2. Since this distance is small, and these two are small values here, because my x2 is its distance from mu of x is small, this one is going to be a smaller positive value and this one is going to be a larger positive value. But nonetheless, both of them are going to be positive. So let's take an x3 here, right? Similarly, this will be my x3, this will be my y3. Similarly for x3 comma y3, this is going to be negative and this is going to be negative because it is on this side, it's on the left of mu of x and this is below my mu of x. But it will still be positive, but it will be a larger positive. right? Now, if I sum up all these positives and take average, the overall value is going to be positive. So I can argue that if my data set is like this, my covariance between x and y, in this case, my covariance is going to be positive, right? And if I have a lot of points which are very, very far away from mu, right? If I have a lot of points which are farther and farther away from mu, I'm going to get a larger positive value, right? Now let's see what happens in a case like this. So let's see what happens in a case like this. In a case like this, let's say I have my point here. Let's assume this is my x1, y1, right? Which means here will be my x1, here will be my y1. Now, x1 minus mu of x is going to be positive. This first component is going to be positive. What about y1 minus mu of x? That's going to be negative, right? So positive multiplied by negative is going to be negative. What about a point here? Right? Let's call it x2, y2. x2, y2. Now for this point, this is what your x2 is going to be, and this is what your y2 is going to be. Of course, your x2 minus mu of x is going to be negative, and your y2 minus mu of x is going to be positive. So overall, it's going to be negative. So your covariance between random variables x and y, if this is the relationship that they have, is going to be negative. Of course, it's going to be more negative if points are more farther away from me, right? So what we understood from here is if x increases, y also increases, then the covariance between x and y is going to be positive. On the other hand, if the relationship between x and y is such that as x increases, if let's say y reduces, its covariance is going to be negative, right? But covariance can be very negative or very positive. I don't know, but if somebody tells me that covariance between two random variables is 5, plus 5, I don't know whether that's a large number or a small number, right? Because, but all I know is that yes, as x increases, y increases. The sign of the covariance is helpful to determine that as x increases, y increases, or vice versa, but not by how much, right? One big problem with covariance is, so let's assume let's assume I have my random variables x and y, where x is heights and y is weights, right? So let's assume this is height. So suppose this is height in centimeters and this is weight in kilograms, right? So from this, let's assume I create two new random variables, x dash and y dash, where x dash is nothing but height in, let's say, feet, and y dash is nothing but weight in pounds or lbs, right? Now for the same data set where you have n observations, these two covariances may not be same. So by just changing the way you measure the same physical phenomenon, your covariances may not match, which is one of the big drawbacks of covariance. One of the big drawbacks of covariance is if I just change the way I measure, it's the same data set, it's the same students, S1, S2, so on and so forth, Sn. For each of the students, we are measuring height and weight. If I just change the system, the metric system, if I just go from centimeters to feet and kilograms to pounds, my whole covariance may not be exactly the same. But we want it to be similar, right? And the way to fix it is using Pearson correlation coefficient, which we'll see just now.